Looking at our next topic in Chapter 1, Section 3, we're going to look at factoring. Now, when we see a number like 18, where did that number come from? Well, several ways. We could have multiplied 9 times 2. We could have multiplied a -3 times a -6, or 1 times 18 to get the product 18. And these items that we use to multiply are referred to as the factors of 18. So there's various factors. So this is what we're going to be doing in this section, is taking a look at this. So for instance, if we look at this example here where there's 15m plus 45, can you see in the number part, the coefficients, that there's a common factor of 15? And that it looks like this after we factor out that common factor. We had mentioned this before when we said we distribute this to get this, and that we will be reversing that. And this process is called factoring. So as we look at example 1, we're asked to take the greatest common factor out of these two terms. Now notice they're both even, so you might think, well, I could take a 2 out of each term, and then I would get 6p minus 9q. Now looking at the items in the parentheses, we see, wait a minute, there's still a common factor of 3 there. So the common factor that you could take out of both of those is actually a 6. So when you do take the 6 out, notice what's left inside the parenthesis. There is no longer any common factor. So you have taken out the greatest common factor. So in example B, as we look at the numbers 8, 9, 15, you could take a 3 out of these, but not out of there. So there are no common factors as far as the numbers go. But then when you look at the variable, you see an x cubed, x squared, x. There is a common x that I can take out of each one, and that's what I illustrate here. Now notice if you distribute this, you get back to what you start with. And inside the parentheses now, there are no more common factors. In letter C, our common factor, as we look at it, is actually a binomial. So we can take out, this is to the third, this is to the second, we can take 2 of those factors out, and it leaves us with this, and then we're left with a 5 and one of the binomials, and then a 2. So we would distribute and then later combine common terms, like terms, and our final answer is what we have down here. This one's a little more challenging. One of the other main type of factoring that we'll be doing is factoring quadratics, where we had a trinomial that came about from multiplying 2 binomial factors. We use the FOIL to do this, to get this trinomial. So we're going to undo the FOIL, that is, work the FOIL backwards. So let's look at the strategy that would be involved. You may recall that the standard form for the quadratic expression is this. And right now, as we look at the one they want us to work with, our a term is a 1, so we don't usually write the a term. And it is then in standard form. Are there any common factors? And the answer is no. So then we put two sets of parentheses because we want to undo the FOIL. Now in our first position, what could go there? Well, only the x. So we get started on the path of factoring this. Now we look at the last term, our c term, and it's 18. Now we want to get factors of 18 that when we multiply these factors of 18, they produce an 18, but now we're going to add up to a 9. So we start listing the factors. 1 times 18. We do this mentally. That's going to be a 19 if they add them up. Well, how about 2 times 9? That adds up to an 11. How about a 3 times 6? That adds up to 9. So we try it. We put a 3 and a 6 there. And then we look for the signs. Well, they're all positive. So we can just put all positives here. And then when we do our outers, we get a 6x. And we do our inners, we get a 3x. That gives us a 9. So this is the factoring of it. And we always check by foiling to see that we get our trinomial. So in example 3, we see that it's in standard form. There's no common factor we can take out of each one. And now we just put two sets of parentheses and undo the FOIL. When our a term is 1, this is easy. This will just be x and x. Now we're looking for factors of 10 that somehow produce a 3 when we add them or subtract them. And that one's easy. It's going to be a 5 and a 2. And our middle term is 3, a positive 3. So our 5 would be a positive, and our 2 would be a negative. And when we do our outers, we get a positive 5, our inners a negative 2, and this one checks. Now in example 4, we notice now our a term is not a 1, it's a 4. So this makes it a little more challenging, but again, there are no common factors. So here we use what is called trial and check, guess and check. So we know there's going to be a y there and a y there. And this 4 could have the factor of 1 and 4, or a 2 and a 2, or a 4 and a 1. Now, often it isn't the 4 and the 1, although we have to keep that in mind. So let's just try a 2 and a 2 here. And then now, again, we want an 11 for the middle. And this is negative, so one of these is going to be negative 1 positive. I'm going to study this a little. Well, after fiddling with that for a while, I realized I didn't copy it down correctly. Yes, you have to copy them correctly. So this wasn't a negative, it was a positive. So we need two negatives here, so that our product here will add up to 6. But then when we do the inners and outers, it adds up to 11. So I had worked this out on the side, and I realized if this is a 3 and this is a 2, Then when I do my outers, I get a negative 8y. My inners, a negative 3y. And then it adds up to a negative 11y. And this one now checks out. But again, I had copied it incorrectly, and that was a challenge. All right, going on now to example 5. And again, with 3 terms, when our A term is not a 1, it gets a little more challenging. So I'm kind of jammed up for room over there, so I'll put it over here. So when you have a 6 as your A term, and by the way, you could put your P there, a P there, and since we're introducing another letter, this will be a Q, and this will be a Q. So now we have both negative, so one of these will be positive, and one of these will be negative. So we've set up sort of what we could without really doing any figuring yet. So what are we going to use? A 6 and a 1, or a 3 and a 2? Well, this number looks a little small here. So for a 6 and a 1, and this one's a 5, well, that's going to be a challenge. So let's use a 3 and a 2 here for our 6. Now, where do we put the 5? Well, our middle term is a 7. So if the 5 is there, and this will just be a 1 there, here our outers are a negative 3. Our inners are a positive 10, but we need a negative 7. Here I'm getting a positive 7. So what I need to do, I tried it that way. I am going to reverse the signs, make this one negative and this one positive, and then try the FOIL again. So now a positive 3, a negative 10, and this one works. Now, of course, the answer is right down here in all of these when you're using your textbook. So keep in mind, going back to the textbook and reading it and studying it is a good idea. In example 6, it is set up in standard form. You try it in various ways, and none of them produce this results. So when you've tried it and you can't get any results, we often say this is prime. And cannot be factored. Now, we did mention in an earlier course that there are special products. One of the special products was when we multiplied conjugates, A plus B and A minus B. When we did that, the middle terms canceled out and we ended up with A squared minus B squared. This is called the difference of squares. So if you recognize you have difference of squares, that will factor into its conjugates. So in example A, we see this is the difference of squares. So we set up our two parentheses and then take the square root of each term. This will be 2m. This is going to be a 3 and a 3, and 1 will be plus and 1 will be minus. And again, you can FOIL, but often it's not needed. Now here we see the difference of something, but they're not perfect squares. So in a case like this, you might say, is there a common factor that we can factor out of each term? And the answer is yes. You can factor out a 2. Now these are perfect squares that will factor into their conjugates. Now as we look at example C, we see our first term is a perfect square. Our second term is a perfect square, but it's not the difference. It's the sum of perfect squares. Sum of perfect squares cannot be factored. So this is something you'd have to keep in mind. All right, in this letter D, when we look at letter D in a modified way, we can think of it as the difference of two squares, but now our A is actually a binomial, so we're sort of substituting. When we factor that, we would get A minus 7, or plus 7, I like the plus first. A minus 7, there we go. Now what is our A? Our A is actually x minus 2. So we put that in there, x minus 2 plus 7. And then our A here is x minus 2 minus 7. Now we just collect like terms, x plus 5 and x minus 9. And of course they show the work in our book. Now another special kind of factoring that we had was when we were foiling a binomial and we get a trinomial, which we call a perfect square trinomial. And if the first term's a perfect square and the last term's a perfect square, and if you were to take the square root of this, which is 4, and the square root of that, which is 5, multiply these two together, get a 20, double it, get a 40. This is a perfect square trinomial. You can recognize that will factor into something like this. So this will be a 4p. We're going to use our negative sign and get 5q. And if you did that special technique where we square this term and get 16p squared, multiply these two terms together, get a negative 20pq, double it, get a negative 40pq, and then you square a negative 5q and get a positive 25q squared. This is recognizing that you have a perfect square trinomial and it will factor into a binomial square. Now in letter B, we look at our first term. That is a perfect square. 1 is a perfect square. But when we take the square root of 9, we get 3. 3 times 1 is 3. Doubling it is a 6. This is not a 6. So therefore, this cannot be factored. This one is prime. In letter C, we see here, this is a perfect square, this is a perfect square, and we give it a try. This is 13x. Our middle sign is plus. This is going to be 4y squared. We multiply these together and we double it and we actually get 104. So this is the factoring of this perfect square trinomial. All right, let's go on to number 9. As we look, is this in standard form? And the answer is yes, but is there a common factor? Yes, so we factor out that common factor, and then we have this to factor. So it would be 2 6x squared minus 13x minus 5. So again, 2 sets of parentheses, and we're looking what will be our A term here. Again, it's often not a 6 and a 1, although if other things don't work, then you would try that. We're going to go for 3x and a 2x. Now 5 is prime, so we're looking for 13. Well, if I put the 5 here, my outers give me a 15. My inners will give me a 2, and that adds up to 13. If this is negative and this is positive. Now, I did that one rather quickly. Again, I have some skill at this, and you will develop yours as you practice. And there are many examples that you'll be doing in your booklet and in your quiz-mes and practice as you prepare for your test. Okay, now as we look at letter B, this is sort of an interesting arrangement, because if you note something, these first 3 terms make up a perfect square trinomial that can be factored into 2c plus 3. I took the square root of that, the square root of that. 2 and 3 is 6, doubled it to 12, and that's what it is. Now I have a situation where this is the difference of perfect squares, and I'll use that technique that I used before to get this, which is in a sense the conjugates that then lead to this. Now in letter C, we see we have 4 terms, and looking at them we realize we could factor out a 4 from each one, which we do here. Now once we do that, again these get complicated, we see here a perfect square trinomial, which we just did one like this before that will factor into this. Now we have the a squared minus b squared in a sense that we will factor this into its conjugates, and we get that. Again, some of these are more challenging, and take your time and study it, and of course you'll practice. Now for our last examples, we're going to take a look at what we call the difference of perfect cubes, and then later the sum of perfect cubes. Now there is a pattern for these, and I will go over it here, and of course your book tells it as well. And when you see you have the sum or difference of perfect cubes, you start off by putting parentheses for 2 terms and parenthesis for 3 terms. This is your step 1 in a sense. Now you look at the sign you're dealing with. Here it's a negative. So you're going to put a negative there. Now over in the middle of the 3-termed parenthesis, there's going to be a sign, that's opposite this sign. So if you put a negative there, from there, you're going to put a positive there. So you set it up now. Now what you do is you take the cube root of this first term and put it there, and the cube root of this term and put it there. Now you square this term, multiply these two together, disregarding the sign because you already have the sign. This is going to be AB. And then you square this term. And that is the factoring of the difference of perfect cubes. Now the only difference between this one and this one is when you are doing the sum of perfect cubes, this sign will be positive, and the opposite sign here is negative. Everything else is the same, and that's the pattern they're showing you. So let's go on to do this one. Again, a parenthesis for 2, parenthesis for 3. What's my sign? Negative. So over here we're going to put a positive. Cube root of that is k. Cube root of 8 is 2. Square the k. Multiply these two together, get 2k. Square this, and you get 4. Now again, what gives a problem for some students, your multiplying should be a negative. But again, we've determined the sign, so that part of it doesn't hold. So whatever sign is there goes in the parenthesis for 2. Opposite sign there, and then following that pattern. So in letter B, again, the pattern is parenthesis for 2, parenthesis for 3, whatever sign is there, opposite sign there. Parenthesis for 2, parenthesis for 3, whatever sign is there, opposite sign there. And then follow the recipe. Now for example 11, they're just saying we can use substitution sometimes. We used a little bit of already. But here this is just going to be x to the 4th. X to the 4th. This is going to be a 3 and a 1. And these are all going to be plus. So that one's straightforward. You could have substituted this and then later, replace what you substituted as we did. In letter B, as we note, we could just factor that, x squared, y squared, y squared, plus, minus. But notice now, again, you have still the difference of perfect squares. So you would have to factor this into that. And in doing something like this, again, this looks like the difference of perfect squares. You could do it straightforward or substitute a little bit if you like, and then keep it in mind again, this is the difference of perfect squares that still has to be factored.